All right, so let's continue. So that was about scalable computing. Now let's go back to the topic of the chapter 4 of the textbook, which is on classification. So with classification, what we do is predicting the class Y, where this can be a member of some set, let's say set A, where the number of entries in set A is, let's say, capital K. And we also have the input X. So X is some vector with X1, X2, let's say all the way to X sub P. So this means that we have a data set, maybe something like this. We have, let's say, X1, X2. I guess this is enough for the sake of demonstration. And we have Y, which is a discrete variable. So I can also write categorical. So, and this is just the number of samples. So we have like the first data point, X1 is some measurement. So maybe it's, let's say 1.5, X2 is 40, and Y is just some categorical variable. So if this is about fish, X1 can be length of a fish, and X2 can be weight of a fish, and Y would be whether this fish is a salmon or a tuna. So we have, let's say, another data point. So 3 meters and 100 kilograms, it's a tuna. And of course, there are salmons of different sizes, tunas of different sizes, but their distributions, are kind of different. So we have, let's say, a large salmon, and then we can also have, let's say, small tuna, which is just, let's say, also 50 kilograms. So now the task here is using X to predict the type of fish. So here, Y is not a quantitative variable anymore. So what we want is some function C that when we apply it to input X, which is a vector of input, it gives us some class K. And K is a member of this set of possible classes A. So this is pretty much what we want to do in terms of making predictions. We want to know which class a given input belongs to. So this is for prediction, but we can also predict or estimate the probability that input X belongs to class K. P sub K of X is the probability that Y equals K, given that I can write it like with a small x to represent an instance rather than the variable when X is X. So let's say in terms of a fraud detection classifier, we have transactions. They are from different times. They have different values. And they are either valid or fraudulent, right? They are either authorized by the actual, account holder or credit card holder, or they are some fraudulent transaction by someone who's trying to illegally move some money between some accounts, right? So based on whether it's, at a normal time and some kind of expected value, we may just pass it as a predicted valid transaction. But if you have tried, using your credit card, maybe in a new country, maybe the first transaction you will get, it will be flagged because they don't expect you to be in Albany, for example, right? Or if you use your credit card for payments of 2-digit values or 3-digit values or a couple of tens of dollars or hundreds of dollars, and then suddenly you go to make a larger payment. Maybe you want to buy some fancy laptop, and you use your credit card for $6,000. Maybe that will be flagged, right? And it doesn't work. Probably you will get some notification on your phone checking whether it is you actually authorizing that transaction, right? So that's another case of making a prediction. Another case of classification, because there are two possible outcomes. There are two possible labels, valid or fraudulent. So this part of classification is pretty easy. This part, estimating probability of classes, is a bit more difficult. So we're going to talk about methods that provide both of these. So you may remember linear regression, right? So linear regression, we had some y hat. This is from previous lecture. We had some y hat that was beta 0 plus sum of some beta I times xi for 1 all the way to dimension p, because we had p predictors, right? Now, if we want to use this for the case where y is discrete, it's not going to work that well. So let's say for binary classification. So for binary classification, let's say we have y, some discrete outcome, which is either 1 or 0. And then we have x, which is just continuous, some x1. So this is just univariate. So data points that we may have could be something like this. There's going to be many of them here because y can only be 0 or 1. And maybe, so this is the scatter plot that we would get in case of a categorical variable. So if we want to fit a regression line, just normal regression, maybe it fits like this. Maybe this is the ordinary least square line for this. So linear regression is going to do an okay job for predicting the classes, but for predicting the probabilities, it's going to be terrible. Because if this line is meant to give us p hat, you can see that sometimes this p hat becomes negative, right? And sometimes exceeds 1, right? So for all these cases, if the input is here, it's going to give us some probability that is more than 100%. That's why that's why linear regression is not suitable for this task. So let's try something else. So the alternative that we have is logistic regression. Logistic regression is based on the same idea. So we calculate this, but then for predicting p hat, which is probability of class 1, we're going to use some fraction. Actually, we predict this, the probability of y being equal to 1 over 1 minus probability of y being equal to 1. This is what we estimate, and we estimate this by using exponential function for this, meaning that we calculate this, but then we raise e, the Euler number, to this power. So in the numerator, we have e to the power of this, to the power of beta 0 plus sum beta I xi from 1 to p. And in the denominator, we have 1 plus this. So this is logistic regression. And logistic regression is going to actually give us some curve like this, which does a great job for predicting or estimating this probability. Because as you can see, it's kind of fitting these data points quite nicely, much better than the line we had. But also, it's not going to estimate any value larger than 1 or any value smaller than 0. Because if this exponent goes to infinity, then this whole thing becomes 1, right? So when this linear part, this linear term, goes to infinity, this whole fraction goes to 1. That's here. This thing doesn't exceed 1. And if this exponent goes to minus infinity, this becomes very close to 0. And this becomes very close to 0. Therefore, we get 0 divided by 1, which is 0. That's here. So that's why logistic regression is going to kind of meet the requirements we have for making predictions there. Yeah?
I'm sure you have 1 minus p there, and 1 plus. Something happened there.
No, p is not this. This fraction is not same as this fraction. Yeah. So you might have heard of the concept of odds, right? Do you know what odds people say? What's the odds of this? You have good odds, whatever, right? What does it mean, odds? Is it probability? So very close, but actually odds and probabilities are not the same thing. So when we say odds of something is, let's say, high, so when odds is, let's say, 9, this means probability of that thing happening divided by probability of that thing not happening is 9 to 1. So this is p of y being equal to 1, our horse winning the horse race, over 1 minus probability of this, which is our horse not winning the race. When this is 9, it means that we have 90% probability over 10% probability of the other outcome. That's why we got 9. So very close. Odds of 9 is equivalent to probability of 90%. But they are not exactly the same thing. So what we're doing here is estimating the odds. We are estimating the odds, and yeah, for that estimate, we use this. So let me just make sure that I didn't make an error here. Yeah. Actually, I made a tiny mistake, but most of these are already correct. So there's this part. We either need odds or these exponents. One of them. I kind of mixed them up a bit. So in here, essentially, what we have is just the numerator. So this is the probability that y is 1. That's it. And then we have something else. We don't really need it as long as we use this. As long as we use this, this is sufficient for our purposes. But we can write this differently, and that would be this estimate. Log of, so it's the log of odds that we estimate using the direct linear term. So this thing then becomes estimated as beta 0 plus sum of beta I xi from 1 to p. So these are equivalent. We either estimate log of this weird thing, which is odds of the class that we want. And for predicting odds of something, as it is 9, it's not a percentage anymore, we can just use normal linear regression because we're trying to estimate 9 or some number, which is okay. The alternative explanation is that if we want to predict probability, we need a fraction because the prediction should give us something between 0 and 1, and this is a fraction that gives us something between 0 and 1, regardless of whether this goes to minus infinity or plus infinity or whatever. So I guess this should be now sufficient for understanding how logistic regression works. So yeah, so this is called log odds because it's a logarithm of odds of something. Another name is logit. All right. So, all right. Now that we have this, as long as we have these estimated parameters, we can make predictions using this model. So, let me just give you an example so that we make some predictions. All right. So let's say we use logistic regression on some data set and we get a table like this for the estimated parameters. We have an estimated parameter for the intercept, that would be beta 0. Then we have, let's say, an estimated parameter for balance. This is the credit card balance. This is some, x1 was the variable balance. That's why we need some coefficient for it. So these are values of beta I. So this is essentially when I is 0, we have intercept. When I is 1, we have coefficient for x1. And then we have, let's say, we have some categorical variable like student status. So we have in our data set something like this. x1 is balance. And x2 is whether that row in the data set represents whether that's a student or not. And then and then we have the outcome, which is whether they default or not, whether they fail to pay for their credit card balance or not. So let's say one row in the data is someone who has $1,000 balance on their credit card. They are not a student and they didn't default. Someone else, $500, student, didn't default. Well, most people don't default, right? Defaulters are rather uncommon. So another non-student who didn't default. And then maybe somewhere in the data set we also have a defaulter, right? Maybe it was someone who has a large balance, and let's say they were not a student. And we have this all the way to n data points. So then when we estimate the parameters, these columns kind of correspond to these rows. Then let's say the coefficient that we have for these and p-values. So the coefficient for the intercept is not that important, but let's say I'm just copying the example from your textbook. Let's say that's minus 10. The coefficient for balance is 0.005. The coefficient for student is minus 0.64. And let's say all of these are significant. As you can see, for all of these p-values, they are smaller than 5%. Therefore, all these variables are relevant for making predictions using this model. Now, this model is essentially this. Probability of defaults is probability of y being equal to 1. So this is what we're trying to estimate. As it is a probability, we need a fraction. In the numerator of that fraction, we have e to the power of minus intercept plus beta 1 times balance plus beta 2 times, whether the dummy variable for student is yes or no, is 1 or 0, over 1 plus e to the same thing. So minus 10 plus 0.005 balance minus 0.64 student. So now that we have this model, I can give you some test data so that you make predictions, right? So we can just check, what is the probability of balance for someone with these features. So for someone with a balance of, let's say, $1,000, who is, let's say, who's a student. right? This is someone with a balance of $1,000 who is a student. If we want to calculate this with this model, it's going to be a fraction. In the numerator, we have e to the minus 10. And then $1,000 will be multiplied to this, right? So we get 5, right? And then as they are a student, there's this. So you can use a calculator and check this value. Anyone has a calculator? No? You need a calculator for your midterm. So make sure to have one, otherwise there will be questions that you cannot answer. Unless you can do this just by a pencil and paper. All right, I'm going to also try. So it's e to the minus 565. $64. You have it? Sorry? It's a bit, so it's like 10 to the minus what? 5? 10 to the minus 3. So, are you sure? Oh yeah, I forgot the minus sign. Minus 564. So the numerator is 0.00355, and we better keep these digits. And the denominator is 1. So this will be 10 to the minus 3, right? So this means that the probability of a student with $1,000 balance defaulting is 1 over 1,000, right? But what about someone with a balance of 2,000? I guess it's going to be totally different. So someone who has a balance of 2,000 and is not a student, it's going to be e to the minus 10 plus that, right? So it will be minus 10 plus 10. Actually, it's going to be very easy, right? E to the 0. I didn't know that I was giving such an easy example, but it turned out so nice. So this is, sorry? This is 0.5, right? This is a half because this is 1 over 2, so a half, so 50%. So someone who's not a student and they have a balance of 2,000, they're going to have a 50% chance of default. So, you know, maybe if this is some credit card applicant from their history, from the history of their credit card transactions, we get some estimate of this. And we ask them, are you a student? They say no. Then our machine learning model says this person is going to have a default rate of 50%. So then maybe we don't accept their credit card application. All right, what about someone with a credit card balance of 3,000? I guess this becomes e to the plus 5 minus this. So e to the 5 is 2.7 to the power of 5. So it's like 40 something, I guess, even more, maybe 60 something over 1 plus 60. So it's going to be 99%, 98% or so. So someone with a credit card balance of 3,000, who's a student, is going to have a default rate of 98%. So that's how logistic regression can be used for making predictions. Now we have the concept of confounding. So now with this data set, if we visualize if we use first two different models. So let's say we have a model 1 that is a logistic regression of default where x is just one dimension, which is only whether someone is a student or not. So this is a univariate logistic regression. And you know, this kind of gives us just a line because one person is either a student or not. And so a student may have, this is the probability of default, which means estimated probability of y being equal to 1. And for someone who's a student, we get this line. For someone who's not a student, we get this dashed line. So maybe for a student, the probability is, let's say, 0.1. For someone who's not a student, the probability is half of that, 5%. For a student, 10%. So this is just based on model 1. And then we have some model 2 that, again, predicts probability of default. But now this is multivariate regression. So it looks at balance and whether someone is student or not. Now on the x-axis, we can have balance and also draw model M2. So model M2 is going to look like this. Again, we get some solid line for student and a dashed line for not a student. So what happens here is that the univariate regression, which are these horizontal lines, are telling us that being a student is kind of a disadvantage for being a credit card defaulter, because students have a higher chance of defaulting. They have a likelihood of 10% of default compared to 5% for the population of non-students, right? But this univariate regression suffers from confounding or confounded variable. So what happens here is that, you know, being a student or not being a student matters because this one was significant. So it is a relevant variable, but its effect size, when it is multiplied to 0 or 1, becomes a smaller component of this prediction. You may remember that here, the balance gave us a value like 5 or a value like 10, a value like 10 in here, sorry, compared to 0.64. So balance eventually is more important than whether someone is a student or not. And what happens is that here, while balance is not included in the model, it somehow has its effect through the variable student, because student and balance, being a student or not being a student, and the amount of credit card balance you have some correlation. Probably students generally have higher balance, right? As students have generally higher balance, when we look at the univariate logistic regression models, students are going to have a line above non-students. But this is not for the sake of being a student. Nothing naturally is making the students more likely to be defaulters other than their balance. That's why when we include balance in a more complicated model, in a multivariate logistic regression, balance will have the chance to express itself directly, and then it's not going to confound student anymore. Then in this model, we're going to see the impact of balance directly and impact of being a student directly. The impact of being a student in a multivariate regression is that the solid line for student is below the dashed line for non-students. This means that generally, being a student should be a positive feature for the bank when approving a credit card application, because when balance is taken into consideration, students are more reliable in terms of paying their credit card debt. Despite the fact that the univariate regression, the univariate logistic regression, kind of shows students to be not the better type of applicants, not the more reliable type of applicants. And what matters is actually the balance, because you can see that when X changes, Y changes quite rapidly. So pretty much the main effect is from balance. So someone who is a credit card defaulter, chances are this outcome is because of their balance rather than whether they are student or not. So this is the concept of confounding, which means that whenever we have a simple model like M1, which only takes into account one variable, and we have, you know, reasonable doubt that there could be other factors involved, we need to include those factors in the model so that they don't confound the current variable. Because it's kind of a reasonable assumption to say that students generally have a higher balance, right? Therefore, we need to include balance in the model so that the variable student measures and represents exactly what it should represent, whether someone is a student or not, and nothing else. So now we have a model that kind of tease out the impact of being a student and the impact of balance. Any questions? No? All right. So let's take another 5-minute break, and then we will continue.